In this lecture, we will define an algorithmic variant of entropy that is commonly known now as Kolmogorov complexity. So in the previous lecture, we looked at entropy from the probabilistic and information theoretic point of view, so namely through random variables. Now we're looking at it from the computational point of view. As I just said, so we defined first an information measure I for random variables or probability distributions. And then we defined entropy as the expected information. So as the average of the information function over the possible outcomes of the random variable. That is always, makes entropy always a property or a characteristic of a distribution or a random variable. But we could also ask if we can define the information content of an individual object. And in particular, can we define the information content of an individual string, finite string? So one way to do this would be to just put a probability distribution on the set of all strings of length n, and just say we take the uniform probability distribution. That means the probability for any string lambda, so the probability lambda of sigma would be 2 to the minus n. But that would in turn mean that all strings have the same probability and hence share the same information content. But this somehow runs contrary to our intuition, since we would expect that the string, let's say of all zeros, where this is a very long string of all zeros, has low information content, while let's say the outcome of a coin toss encoded as a 0-1 sequence should have high information content. And you may wonder why we would say something random has high information content. We will justify this later on when we equate information content with compressibility. So the less compressible something is, the higher the information content, and a coin toss we would envision as something hardly compressible at all, actually as incompressible. So now one could ask, well, the uniform distribution obviously doesn't work for this. Maybe can we find a different probability distribution on the strings, such that simple strings have high probability and complex strings have low probability? Because by the nature of our information function, right, we call that was minus log the probability. So if we have high probability, that would mean that the information would be low, and complex strings would have low probability, which means in turn high information. And we will see later that this is indeed possible. But before we do that, the way to get to this probability distribution is easier if we first define a different complexity measure, and then later try to recast this as a probability distribution. So the basic idea, as I already said, is to equate low information content with high compressibility. And Kolmogorov complexity makes this idea mathematically rigorous. And it builds on the framework of classical computability theory, as we have studied in lesson 2. So we take M to be a Turing machine, and we suppose now our Turing machines work on always on binary inputs and binary outputs. And so suppose we have a string, a finite binary string sigma. And now we set C sub m, so the complexity of the string sigma with respect to the machine M is the minimum over all length of strings P, where if we input P into M, the output is sigma. So again, C sub m is the length of the shortest program, or a shortest program. There can be several shortest programs the length of a shortest program that when fed into M outputs sigma. So it might be for a particular M that there is no program that produces sigma. In that case, we just set the complexity to infinity. So once again, so the M complexity of a string is the length of the shortest M description. So you can think of this P as a code for sigma with respect to the decoder M. So think of this as P is the code, and M, right? M is the decoder, right? That decodes the code P into our output sigma. But there's a problem with this definition. There is, of course, a certain arbitrariness in the choice of M, right? So because different machines can assign the same string drastically different complexities, right? So for instance, we could have sigma, a very complicated string, so very complex, and for one Turing machine M0, it takes a very long program to actually compute this. So it has a very long program. But there's another Turing machine M which has sigma in the memory, so it essentially burned in, sigma burned in, and it has sigma in this sense. To produce sigma, it just needs to look it up in the memory and just tell, well, just output what I have in the memory, and hence it has a very short program for sigma. So in this sense, these two Turing machines assign sigma of drastically different complexities. So does that not mean that the definition, although sound for a single Turing machine, overall as a measure of information content is doomed to failure? Well, as we'll see, if we use a universal Turing machine, then we can actually take care of this problem. We can never kind of get all the complexities completely in sync, but at least we can get everything within an additive constant. As a universal Turing machine can actually simulate all of these machines, and hence it takes into account all of these different complexities. So in order to use a universal machine for the definition of Kolmogorov complexity, we need a pairing function for strings. And one way to do this is very simple. We just code a pair of strings sigma tau into one single string by first giving a number of zeros, and the number of zeros depends on the length of sigma, so the first string in the pair. Then to indicate that now the coding part that codes the length of sigma is over, we put a 1 in there, and then just list sigma and tau. So now there's an easy algorithm that just, if we read this, can recover sigma and tau from it, because we just need to tell the algorithm to say, well, read till we have hit the first one, count the number of zeros up to that point. That tells me how many bits after the first one I have to read to get sigma, right? And once I've read sigma, well, I just need to read the rest of the string to get tau. Since we universal machines work with Gödel numbers of other machines, so indices of other machines, we can also identify the natural numbers with their binary representation to put it into this framework of strings here, right? So note that then the length of the binary representation of the natural number n is about the binary logarithm of m. Okay. And now recall that a universal Turing machine U emulates all other Turing machines. So if we have a Turing machine with Gödel number E, right, then the universal Turing machine on input E comma sigma as a coded pair gives us the computational result of M sub E on sigma. And now what we do is we fix any universal Turing machine. We will see in a second that this doesn't really matter which one. And we define then the complexity of sigma to be just the U complexity of sigma. So the complexity of sigma with respect to that universal Turing machine we fixed. So the reason why choosing or working with a universal machine and the independence of the choice of the universal machine, the particular universal machine, both lie in the following theorem, which is known as the invariance theorem, and it's due to independently Kolmogorov and Solomonov, discovered around the same time, 1965, 1966. So what does the invariance theorem say? Well, for any Turing machine M, there exists a constant Cm, and it's important to note that this constant only depends on the machine. So there exists a constant Cm such that for all strings sigma, the Kolmogorov complexity of sigma, so the complexity with respect to our fixed universal machine, does not exceed the complexity of M, so the M complexity of sigma, by this constant Cm. So that means that up to a constant, the universal machine compresses just as well as the any particular machine, other machine M. And if, in particular, if M is another universal machine, right, then that means that the Kolmogorov complexities defined with respect to these two different universal machines differ by at most a constant. So if we're willing to accept that we can only define, or we can define information content for strings only up to an additive constant, then this definition is perfectly sound and works well and gets rid of this arbitrariness. However, we cannot get rid of this constant. So everything is only works with like an additive constant. Now the proof of this theorem is very simple. So suppose P is the shortest program with respect to n for string sigma, and E is the Gödel number for of M. So that means M is equal to M sub E, right? But now since U is a universal machine, that means U of E comma P is the same as M of P, right? So that means now E comma P, this coded pair here, is a U program for sigma. And that means the Kolmogorov complexity of sigma with respect to the universal machine, right, is at most the length of this coded pair. But what is the length of this coded pair? Well, it's the length of this string as we define the coding of pairs, right, which is this expression here. But what is the length of this expression? Well, we have length E many zeros, right? That gives us length E, right? And then we have a 1, that gives us a 1. And then we have E, but remember we identified natural numbers with their binary representation, and then the length of that representation is about log E. So we have log E, and then we have P, so plus the length of P. Right, so here remember this one, again, because we identify this, we get log E. So altogether, we get 2 log E plus length of P plus 1. But length of P is the Kolmogorov complexity with respect to M. So it's the M complexity of sigma. So length P is the M complexity. And then we have these two parts here, 2 log E plus 1. And this is our coding constant, Cm. So this we will choose as Cm. Okay, here this coding constant. Okay, so that's the proof. Very, very simple indeed. Note for notation now, since we'll always be working within an additive constant, we'll use the following notation. So C of sigma less than equal to plus f of sigma, where f is a function of sigma, now means that there exists a C such that for all sigma, C of sigma is less than or equal to f of sigma plus C. So you can also, if you're familiar with the little o notation, you could also write this as f of sigma plus o of 1, right? Big O of 1. So this is also a way to write it. But if you don't know the O notation, the Landau symbols, don't worry about it. We will use this notation, and it's simple enough to define. So let's see if we can establish some basic properties of Kolmogorov complexity. So the first observation is that within an additive constant, the Kolmogorov complexity of a string is always bounded from above by its length. And that's easy to see by just considering the copy machine. So the copy machine just takes the input and copies it to the output tape, so outputs it. That means that with respect to this machine, the complexity of a string sigma is at most its length, right? Or is its length. And hence, by the invariance theorem, we know that the Kolmogorov complexity of sigma then is at most the length of sigma plus an additive constant here. Next, we have that for any n, so here we say complexity is at most the length, but we can see that indeed there are strings of any length that kind of are maximally complex, in the sense that there for any length n there exists a sigma of length n whose complexity is greater than or equal to its length. So these you can think of as an incompressible string. So this sigma would then be called incompressible. And the proof of this is a simple counting argument. Well, how many strings of length n are there? Well, we have binary strings, so it's 2 to the n many. But in order to have a complexity of strictly less than length n, right, the length of sigma, well, you need a program to witness that. How many programs of length less than n are there? Well, there's one program of length 0, 2 programs of length 1, 4 programs, 2 to the 2 programs of length 2, and so on, and 2 to the n-1 programs of length n-1. If I sum all of these up, I get 2 to the n-1, which means that we can, there must be one string that is incompressible, right? Because there are only 2 to the n-1 programs of length less than n, but there are 2 to the n strings of length n. So there must be at least one incompressible string. And we can show that there actually must be much more, right? This is a very crude counting argument. And finally, the Kolmogorov complexity cannot be increased by performing computable operations on a string. So if h from strings to strings is a computable function, then the complexity of the result of the operation, right, C of h of sigma, is at most that of C of sigma, so the complexity of sigma, right? Of course, again, within an additive constant. And that can also be seen very easily. So suppose M is a Turing machine that performs the following, or computes the following function. It takes the universal, what the universal machine does on sigma, and then just whenever this is defined, it just operates h on it, or performs the operation h on it. By the Church-Turing thesis, this is indeed a partial computable function, so it can be performed by a Turing machine. And then by the invariance theorem, the complexity of C of h of sigma, right, is at most that of C sub m of h of sigma. That's the invariance theorem here. But what is the m complexity of h of sigma? Well, if we have a program P that when input in the universal machine, so u of p gives us sigma So maybe I should have used P here instead of sigma. So think of M of P is H of U of P. So if U of P produces sigma, then M of P produces H of sigma, right? So whenever we have a program for U that produces sigma, then the same program will produce H of sigma when fed to M. So the complexity of H of sigma with respect to this machine, right, is at most that of the complexity of sigma when with respect to the universal machine that we use to define complexity. So in particular, this holds if this is the shortest program. So if it's actually a program of length c of sigma. So here we have a program then that witnesses that the M complexity of H of sigma is at most this. And that's actually what we wanted to show. So now we have dealt with the arbitrariness issue of complexity, Kolmogorov complexity, and established some of the basic properties we would like it to have. We can ask a little bit further how robust actually is C as an information measure. And one of the properties we would like it to have is definitely the following: if it reflects information somehow. We would want that the information that is contained in a pair sigma tau. So we write now this C sigma tau to make this a little bit more readable. This is just C of the coded pair sigma tau. So the complexity of a coded pair, so what is the information content of it? Well, it should not be more than the information content that is contained in sigma and in tau, right? So does this hold? So it does hold in the case of entropy, as you can easily see. So for entropy we have this. So if we replace C by H and look at the joint entropy, you can easily verify this. So does it hold for C? And now if we try to prove this, how would we go about? Well, suppose we have a program for sigma, call that P, and we have a program for tau, call it Q. And now we have to somehow combine these two things into one program for another machine, right, that then outputs sigma tau, so the coded pair. Well, of course, what it suggests itself to just concatenate the two things, the strings, into one big string. So call this PQ, and then so this would be one big string R, right? So now, well, couldn't just a machine now just read R? So we have a machine that reads R and then outputs first. Well, once it reads the P block, it outputs sigma, and once it reads the Q block and outputs tau, and then computes the coding pair of the two. So does this work? Well, the problem here is how can M tell where? Well, since M only sees R, right? So it doesn't have any information where the original P ended and then Q starts, right? It only sees a string, a finite binary string, and now it somehow has to guess, right? Where does P end and where does Q end? So what about this boundary here, right? So how does it know about it? Well, it could try different partitions here, but how does it know which one is the right one? So that points to indeed a fundamental problem here, in the sense that our programs that we feed into Turing machines are not self-delimiting in a way, and we will make that precise in the next lecture. So our machine M cannot tell when a certain input here, if you combine two programs into one string, it cannot tell when the one program ends and the next one starts. There's a way that we can kind of take care of this problem by looking at what is called prefix-free programs, and we'll do that in the next lecture. But this argument, hence, will not work to prove this. And we had trouble proving this, and no surprise, because it actually turns out to be false. And that's a consequence of the following theorem due to Per-Martin-Löw. Suppose we have a natural number k fixed, then for any sufficiently long tau, there exists an initial segment sigma of tau, such that the complexity of sigma drops by, or the compressibility of sigma drops by k, right, is less than the length of sigma minus k. So tau can be incompressible, right? It's a long string that is incompressible. That means its complexity is its length, but nevertheless there must exist an initial segment sigma of tau that whose compressibility drops below k. So that's slightly counterintuitive, right? Because you would think that if you have an incompressible string tau, all of its initial segments should also be incompressible. But that's not true. Now, how do we prove this? Let's see. So first, we order all finite strings length lexicographically. So what does that mean, length lexicographically? It just means like we first order by length, and then between strings of the same length we order it like in the phone book, right? So we say 0 is less than 1, just like A comes before B. Okay, so that means the empty string is the smallest one, and then 0 and 1, those are the two strings of length 1 that are ordered in this way, and then 0 0 0 1 1 0 1 1. So the phone book ordering, and then all strings of length 3 and so on. Okay, and we denote by n of sigma the position of a string sigma in this ordering. So for instance, if sigma were let's say 0 0, right, then the n of sigma would be 0 1 2 3. So n of sigma, since we start counting at 0, so n of sigma would be 3. So now we take any initial segment of tau, okay, of our string tau, of a string tau that can be any sufficiently long string. So think of it like this: we have our long string tau, and now we just take cut off an initial segment of this and call it theta. So now comes the trick. This theta will have a place in this ordering because it's just a binary string. So let n be that position in that ordering, n of theta, and let rho be the next n bits of tau. So we take rho here, over here, where rho is the length of rho is n, so we have here n bits, and then we call this whole string together, tau together with rho, we call this alpha. So this here is alpha. So here you see alpha is the concatenation of theta and rho. Now comes the crucial observation. What is the complexity of alpha? So what do we need to reconstruct alpha? Well, we only need rho, right? So because if we know rho, we also know its length, right? That's the n bits. But once we know n, so the length of rho, well, what was n? N was the position of theta in the listings of all binary strings. So once we know n, we also know theta, right? So all we need to construct this whole string alpha here is rho, right? Because again, once we know rho, we also know its length. Once we know the length of rho, we know n, right? Because the length of row is n, and once we know n, we know theta, right? Because n codes the position of theta in this listing of strings, which we can effectively generate. So again, to know alpha, we only need to know row. That means the complexity of alpha is at most row, the length of row plus some constant c. So now we just choose our initial segment theta, so the length long enough, namely longer than k plus c, and then we'll see that c of alpha is at most length of row plus c, but the length of row is just the length of alpha, right, of the long string, minus the length of theta, right, the first string in that part of alpha, plus c. But theta now was chosen to be greater than k plus c. That means this expression then is less than length of alpha minus k, by choice of length of k, of theta, which is exactly what we wanted to prove. Here's our initial segment that is k compressible. So now we can get the failure of subadditivity as an easy corollary of that theorem. Namely, for any d, there exists a string tau, which is a concatenation of theta and sigma, such that the complexity of tau is greater than the complexity of theta plus the complexity of sigma plus d. And now you only need to kind of observe that, well, what the complexity of theta concatenated with sigma is at most that of the complexity of theta comma sigma. Because if I can produce the pair, I can also produce the concatenation. So here, from this, right, we get the failure of subadditivity. So for any possible additive range in which those two expressions could be, right, we get a counterexample in the form of this tau here. Well, how do we prove this? Well, now we use the theorem. First we pick a c such that all complexities of a string alpha is at most length of alpha plus c. We saw that was the coding constant essentially of the copy machine. Well, now we choose a sufficiently long string tau that is incompressible, right, whose complexity is greater than or equal to the length, and that has an initial segment theta, whose complexity actually loses this incompressibility by an amount of c plus d. Okay, so we can do this by the theorem. Now we just do the following. We just say sigma now is just the rest of the string, so how to fill up or extend theta to get to tau. Well, then the complexity of theta plus the complexity of sigma, well, the complexity of theta is, by this assumption here, less than length of theta minus c plus d. The complexity of sigma, right, by the choice of c, is at most length of sigma plus c, right, copy machine. Right now, but if we put all this together, we get length of theta, right, length of theta plus length of sigma is the length of tau. Right, and here the c and this c cancel out, so the only thing that's left is minus d, so is less than or equal to the complexity of tau minus d, which is what we wanted to prove. So what went wrong here? So why does subadditivity fail for Kolmogorov complexity? Well, the crucial fact here was that we could exploit the fact that a string not only provides information through its bits, but also through its length. If we recall, in the proof of the theorem a couple of slides ago, well, we took this string theta, right, and then we looked up its position in the listings of the length lexicographical ordering of strings, and then extended right? And then just chose the next n bits and called those row, right? But from row, we were able to reconstruct not only row itself, but since row coded the length of row coded the position of theta in that length lexicographical listing, we could also reconstruct theta from it. So row not only contained the information given through its bits, but also through its length, right? Because it coded theta for us. And this is not accounted for by our function c, right? So now the question is, can we alter the definition of complexity to take this into account? Right? Can we somehow say, okay, the information content should not also reflect the information in the bit, but also the information in the length? And that leads us to a new or an alternative notion of complexity, a variant of Kolmogorov complexity, which is now known as prefix-free complexity, usually denoted by capital K. And we will look at this in the next lecture, and it will lead us back to this question actually that we had: why did the naive argument fail for proving subadditivity? Namely, we could not distinguish, well, where does one input end and the next one start? And that's exactly what prefix-free complexity does. We will always be able to tell this. Where does the input for a machine end?